You can start.
Okay, fine. So good afternoon to everybody and welcome to this last session of OFCM Foundation Course in Mathematics. Okay, so last time we were looking at several examples of 1, 1, 1, 2 functions. So I hope you are comfortable dealing with 1, 1 and onto function, how to check whether given function is 1, 1 and how to check it is onto. And in case it is 1, 1 onto, we also define what is meaning of how to define inverse of a function. Right? And you can also many times you can actually find expression also for the inverse of a function, but that may not be the case always. Okay. So today again, let us look at. So is there anybody who is still having trouble with the concept of 1, 1 onto bijection, etc.? Is there anybody who is having difficulties? You can raise your hand and ask your doubts. Okay, if you don't have any doubts, then we'll continue. So again, let us start with a function f from set x to y, right? We already defined what is meaning of range of f, right? This was collection of all images, right? This, how did we define? We defined this as set of all f of x such that x in x, or this can be defined as collect all the elements in y such that y is image of some x in x, right? Such that there exists x in x with f of x is equal to y. This is how we defined range of the function, right? Okay. But suppose, so let us look at, so this is your x, this is y, and from here to here you have a function f. Now suppose instead of this entire x, we have some subset. A is a subset of x. We want to define what is meaning of f of A, right? Image of elements from A. That's what we want to define. So it should be a subset of y, right? It should be some subset here. This is f of A. So how do we define? What should be the definition? Can you just quickly think? We want to define this as a subset of y. So the moment you want to define subset of y, I will write set of all y in capital Y if something happens. What should go here? Can you just think of? Just think for a few seconds, you should be able to get. You want to collect all those elements in Y with some property. Right? For a particular case of A to be X, we already know. Only one of you. That's okay. So who has said yes? Pratichi, can you tell me what should be, how will you define?
There exists x in A such that f of x is equal to y.
So what should I write now?
There exists x in A such that f of x is equal.
There exists x where? In
A.
In A such that
f of x is equal to y.
Such that f of x is equal to A. That is equal to Y. That's correct, right? So take all those elements in Y such that you can find some X here. So if I take here Y, there is some X in X such that this f of X is equal to Y, right? On the other hand, most of the book will define something like this, right? Collect all the images of elements from A, f of A such that A in A. Okay, f of A such that A in A. Right? Again, since this is an element of Y, this is subset of Y. Okay, right. And this is what we call as image of A. Okay, image of A. Right. So so now you see here advantage of writing this definition. The definition this way is that immediately we know when does an element belong to FA. If I say Y belongs to FA, by definition, it tells me that there exists some X in A such that the image of X is Y, right? This simply means that there exists X in A such that f of X is Y. Okay, but if I look at this definition, it says that the elements are always of the form f of A, right? So that means already we are saying that you take an element in A, whereas we are saying that we are talking about some subset of Y. So elements of Y, if we start with, then if I look at any element Y in capital F of A, this means that there is some X in A such that Y is image of X. Okay, right. Is the definition clear to everybody? Is the definition clear to everybody? So we will always work with this definition. Okay, so 34 of you. Anybody who is not clear about this? Megha? Yeah, see, you have clicked. Okay, fine, let's go ahead. So now let me ask you some simple questions. Suppose I take, let us say my A is empty set. If A is empty set, what can you say about f of A? What can you say about f of A? Just clear all the response. What can you say about f of A if A is empty set? What will be image of an empty set? Yes? If you have understood the definition, it should be easy. Is there somebody in group A who has clicked yes? Group 1?
Nobody clicked yes.
Okay. Group 2?
No one, sir.
Group 3? Rutusri? Rutusri? What is your answer?
So f of A will also be empty
You're saying f of A is also empty. Why?
because when A is empty, f of A in f of A belongs to the set A. So if A is empty, then f of A will also be empty.
Yeah, but you need to prove, right? We need proof from this definition. What happens if f of A is non-empty? There exists some element y in f of a, right?
Yes, sir.
Correct. So if y is in f of a, what does it say? There must exist some x in a such that f of x is y. But a, can an element x will lie in a?
No, it is
No,
empty.
right? So
Yes.
that's why this is empty. Okay.
Yes, sir.
Is that clear to everybody? If a is empty, then f of a is empty set. That is. What about if I say if f of a is empty, can I say then a is empty? A is empty. Right? Can I, if f of a is empty, can I say that a is empty? Right? So what in case a is non-empty, what can you say about f of a? F of a will be always non-empty set, isn't it? Because what is f of a? Collection of all f of a. So if a is non-empty, there is at least one element, let us say some a in capital A such that f of a will lie in f of capital A. So in that case, this cannot be empty. So this is also true. Right? So in particular, this is if and only if f of a is empty, if and only if a is empty. Okay, that is, so this is quite simple to look at. Is this clear to everybody? F of a is empty if and only if a is empty. Is this clear to everybody? Okay, fine. Right. Now let me ask you another simple question. Suppose I have A, which is a subset of B. A subset of B. Then what can we say? And then look at what is f of A and f of B. Okay. What should be the, these are two subsets of Y, right? A is subset of B. And look at f of A and f of B. What can you see? What can you say about FA and FB? What can you say about FA and FB? So as a subset, what is the natural question that you will ask if you have two subsets, whether one is contained in the other, right? Already we are saying that A is subset of B. Yes, Wahiba? Wahiba?
Yes, sir.
Yeah. What should be the relation?
It is given that A is a subset of B. Then the image of A will be in f of B.
In f of B, that means you are saying subset?
Yes, sir. F of A is a
Okay.
subset of.
Okay, so why is that? How will you show this? How will you show this? So if I want to show this, what should be my first step? If I want to show that one set is subset of another, what should be my first step? We have to start with an element in f of A, right?
Yes.
Take an element in f of A, if it exists, right?
Yes.
If there is no element in f of A, what does it mean?
It means it's an empty set.
F of A is empty set. If f of A is empty, then is it a subset of f of B?
Yes.
Yes. Okay. You can mute yourself. Fine. So in case f of A is empty, this is always subset of any set. We already know that, right? So, but in case it is non-empty, then let us take y is in f of A. But the moment y is in f of A, what does it mean? There exists some x in A such that y is equal to f of x. But where does x lie? X lies in A. And what do we know about A? It is subset of B. So since x is in A and A is subset of B, x is also in B, right? Now if x is in B, what does it imply? If x is in B, where will be f of x? If x is in B, where will be f of x? This will lie in f of B, isn't it? For any x in B, f of x will always be in f of B. Okay, but f of x is y. Therefore, we have proved that if y is in f of A, then y lies in f of B. In particular, f of A is always subset of f of B. This is always true. Right? Whatever may be the function f, this is always true. Right? If A is subset of B, f of A is subset of f of B. Is this clear to everybody? Is this clear to everybody? Okay, fine. So just take some 10 seconds and see how will you go through the proof. Don't look at the screen. Without that, try to go through the proof. If A is subset of B, f of A is subset of f of B. Okay, so is there anybody who did not get the proof? Is there anybody who could not complete proof of this without writing? Okay, fine. So let's look at some simple example first. So suppose I take f of f from R to R. Say f of x is equal to say mod x, right? So all of you know how to plot graph of this function, right? We looked at this. I think that's the graph of the function, right? So y is equal to mod of x. Now suppose I take, for example, my set A to be set of, let us say, this is +1 -1. What do you think will be f of A? What will be f of A? So for each element in A, you have to write its image. So what is image of +1? 1. What is image of -1? 1. So this will be what? This will be singleton 1. Okay. Suppose you take A is equal to say -3 to 4. -3 to 4. Can you tell me what will be f of A? What will be f of A? Yeah, tell me quickly. So what is that you need to do? You just look at Now, in this case, somewhere here you have -3, here you have 4. Right? So what happens to where does this image go? Right? This is what this is going to be the image, right? And then you just draw. So this part will be covered here, and this part, this positive side will be covered here. So the total, when I include this and this part, this is going to, what will this be here? This will be 4. This is 3 here, right? So what should this be the answer? Somebody from group 1? Somebody from group 1?
Anushka.
Yeah, tell me.
Closed interval 0 to 4.
Closed interval 0 to 4. That's correct. Closed interval 0 to 4. That's what we saw, right? Goes from 0 to 4. Okay, right. So you can try with the other thing. Suppose I take A to be, let us say, -infinity to, let us say, -1 union, let us say 1 to infinity. What will be f of A? What will be f of A? So -1 to this side we are looking at, and then 1 to infinity. Come on, quick. This should be quite easy, right? So -infinity to -1 open, -1 is open, right? So this will, what will it cover? This will cover from 1 to infinity, isn't it? This side. And this side again, this is from 1 to infinity. So this will cover, sorry, this one is here somewhere. So this will cover from 1 to infinity. So 1 will be included in this case. So this you are going to get 1 to infinity. Nothing between 0 and 1 is going to come. Right. So yeah, this is quite easy. Similarly, let us take another. This is, suppose if I take f from R to R, let us say f of x is equal to x square. Can you tell me what will be image of, let us say, -2 to 4? What will be image of -2 to 4? This open -2 here, closed 4 here. Okay. Right. So again, you can just draw the graph. It's the graph of the function. Here you have -2. Here you have 4. These two are almost very similar to each other, the examples. Yes. Of course, when you have guessed that this is the image, ultimately you also need to justify. This is our guess, but you also have to justify that 2 sets are equal. So take element in one set so that it lies in the other set. All these things you have to do. Okay, so yeah. Is there anybody in group 2 who has clicked yes?
No one, sir.
No one. Chandrendu from group 3?
Sir, closed interval 0-16.
Closed interval?
0-16.
0 to 16. That's correct. Because again, you see why you are from -2 to 0. This is what happens, right? So this will of course it will take 0, and then here this will not take this. What is this going to be? This is going to be 4. My drawings are not that good, but yeah, this is going to be 4 here, right? And this part is going to cover 0 to 16. 0 to 16, right? Somewhere here it will be 16. Okay, so this total, the whole thing is going to be 0 to 16, right? Or how do we show this? So if I take any y in f of -2 to 4, right? We want to check that there exists some x in x such that f of x should be equal to y. But what is f of x? This means x square. X square should be equal to y, right? So that means what? Now, if I take any element in this set, what are x whose square lies between 0 to 16? So that x will lie between -4 to 4, right? So already we will get some element from 0 to 4, right? Of course, in addition, if the y lies between -4 and 4, you will also get somewhere here also. Okay, right. So that's how you can verify. Okay, now let us again play with this this definition. So let us look at. I have again this x. This is my y, right? And suppose I take two subsets. One is, let us say, A, and another subset is, let us say, B, right? I have two subsets. So if I look at this A, its image will be somewhere here, right? This is my f of A. If I look at this B, the image of B will be somewhere here. Let us say this is my f of B. Okay, right. So we want to understand what happens if you take union intersection, right? So what is that we are assuming? A and B are subsets of X. Look at f of A, look at f of B. These are subsets of Y. Now, so on this set X, I can take union, right? A union B. That's again a subset of X. And then I can take its image. So take union, take its image. On the other hand, I already have f of A and I have f of B, right? I have f of A and f of B. So you can take union on of these two sets. Now both this and this are subsets of Y. Both are subsets of Y, right? Okay. So what should be the relation? How are these two sets, how are these two subsets of Y related to each other? Okay, that's what we want to explore. That's what we want to explore. So whether this is subset of this or this is subset of this, or they are equal. Okay, this is what we want to check. Okay, right. So we want to check whether this is subset of this, and similarly whether this is subset of this. F of A union B, is it a subset of f of A union f of B? Right? Okay, so let us first look at the first part. Let me just, so that we can concentrate on one part, let us just look at how we can deal with this. Right? So if I have to show this f of A union B is subset of f of A union f of B, how do we show that? How do we show that? Can you just go through the what argument you will be doing? Just start proving and see whether you can complete the proof. So what will you do? You will start with an element y in f A union B. Let y be an element in f of A union B. Okay. What does it say? If y is in f of A union B, by definition, it says that there exists some x in A union B such that f of x is equal to y. Right? So we have got an element x in A union B. If x lies in A union B, what do we know? X lies in A or x lies in B. But if x lies in A, where does fx lie? Fx lies in f of A. Therefore, but f of x is y, therefore y lies in f of A. Right? What is the second case? If x lies in B, then fx will lie in f of B. Therefore, y, which is equal to f of x, will lie in f of B. Therefore, y will lie in fa union f. So in any case, this is always true. Right? This is always true. Have you understood the proof? Now we are in 12th session, so you should be able to understand these things quite easily. How many of you have understood this proof? Okay, Jane, you have understood?
Yes, sir.
Okay, Manak, you have not understood? Manak?
Sir, I understood.
Okay, so fine. Anybody who has not understood, please raise your hand. Atul?
Yes, sir.
Atul? Yeah, you have difficulty?
Yes, sir, your voice was continuously breaking. I don't know if it's my internet issue.
So did you go through the proof or no?
No, sir, I couldn't hear anything clearly.
Okay, so then we can. Anybody else? Okay, fine. Let us go ahead. All the 34 of you have understood. So in case some of you are still having difficulty, you can discuss this in breakout. Okay, so this is always true. And this is true. And you see, we are not assuming anything about f. This result is always true. Now let us look at what happens to this side. Can we say that f of A intersection f of B, this is f of B, is it subset of f of A? Sorry, let us look at the union itself, not go to intersection. F of A union f of B, is it subset of f of A union B? This is what we want to look at now. This part is always true. We check. Okay. Of course, you can again start with the same argument. Start with an element in the left hand side and show that is an element in the right hand side. You can do that. But actually, we have already proved. Right? See what we proved. We proved that in case A is subset of B, then FA is always subset of f of B. Can you use this fact to prove this? Can you use that fact whenever A is subset of B, f of A is subset of f of B? From this Does it follow? Can you make use of that result to show this? Yes.
How many of you can show it? You say yes or no?
Only one has clicked yes. Only two of you. Yeah, Fatima. How will you show, Fatima?
Sir, let y element of f of a
No. We don't want to go through that. I said, can you use what we have already proved? If A is subset of B, then f of A is subset of f of B. Using that, can we conclude from this? What you are saying is not incorrect. One can show that. But something which we have already proved, we can make use of that. Yeah, so how will you make use of? Anamika?
I just had thought of that method, y element of.
So please listen carefully. Shahjahan?
Yes, sir.
Yeah, tell me.
First I took A as a subset of A union B.
A is always subset of A union B. Very good.
Then f of A is also a subset of f of A union B.
Correct. F of A is subset of f of A union B. Very good.
Similarly, B is a subset of A union B, and f of B is also a subset of f of A union B.
Correct. Therefore,
f of A union f of B is a subset of f of A union B.
Right. Very good. Very good. Right. So, see, I asked you to make use of that. So I want something subset, and the image will also be right. So the natural thing is here, A is always subset of A union B. So f of A is always subset of f of A union B. Similarly, f of B is subset of f of A union B. Therefore, f of A union f of B will be subset of f of A union. Okay. What we are using is, if A is subset of, let us say, C, and B is also subset of C, from these two together, A union B is subset of C. That's what we are using. Okay, so this is also true. Is this clear to everybody? Come on, quick. Sunday response is always slow, right? We are in relaxed mode. Okay, fine. Right. So therefore, both put together, what we have achieved is f of A union B is always equal to f of A union f of B. This is true for any two subsets A and B. Okay, so F behaves very nicely on union of sets. Right. Let us look at what happens if we look at intersection. What happens if we take intersection. So what is that we will be looking at now? Look at A intersection B, and then look at f of this. On the other hand, you have f of A intersection f of B. Okay. Right? We want to check whether this is subset of this or whether this is subset of this or both are true. Again, if you look at one part is again very easy. One part is again very easy. Can you quickly look at whether this is true or no? Again, it follows from something which we have proved. Yes. Something which we have already proved and just now we used. Still only 3 of you. Think. Pratichi?
Sir, A intersection B is a subset of A.
A intersection B is always subset of A. Very good. Yeah. So
A intersection B is also a subset of B.
correct.
So f of A intersection B will be a subset of f of A, and f of A intersection B will be a subset of f of B, which implies that f of A
Right.
intersection B will be a subset of f of A intersection f of B.
Right. That's correct. Have you followed? Is it clear to everybody? Let me clear the response. What Pratichi has said, have you all understood? Okay. Mirna, you have not followed? Mirna?
Yes, sir. Yes, sir. I was going to put the tick.
Okay. But before you put the trick, I asked. Okay, fine. So 33 of you still, few of you have not understood. So let again just repeat what Pratichi has said. Right. So A intersection B is always subset of A, right? And it is subset of B. So therefore, this is going to be always subset of this. Similarly, this is also subset of f of B. Therefore, if A intersection B is subset of f of A and it is also subset of B, therefore f of A intersection B is subset of f A intersection A. Right? So what we are using here is, we are using, if you have set A, which is subset of, let us say, C, and B is also subset of C, and A is subset of, let us say, B, then A is a subset of B intersection C. That's what we are using. Okay, fine. So this is again always true. This is always true. No matter what is the function, this is always true. Fine. So let us try to explore what happens to other side. If I look at f of A intersection f of B, is it subset of f of A intersection B? This is what we want to explore now. Okay, this is what we want to explore. Okay, so now let us try to prove, right? Whenever we want to prove something is subset of that. One set is subset of another set. The usual argument, we start with an element in the left hand side, and we show that it is an element of f of A intersection B. So let y belongs to f of A intersection f of B. Okay, now I will just ask some of you to complete the proof and then see what happens, whether everything goes through. Okay, so can you call somebody from group 3? Group 3, what should be the next step? From this, what should I write as the next step? Somebody from group 3? Mentor, can you call? Yeah. So what do I write next step, Wahiba? If y lies in f of A intersection f of B, what does it mean? What does it imply?
Y belongs to f of A and
Y belongs to f of A and y belongs to f of B. Okay, fine. So somebody else from group 3? Somebody else from group 3?
Ritusri?
Yeah, Ritusri. What should be the next step? If y belongs to f of A, what should be my next step? See, all of you should think. I'm asking Ritusri to complete the proof, but all of you also, along with this, think. What should be the next step? Ritusri. Y belongs to f of A. What does it mean? You're not paying any attention, right? Chandrendu? Chandrendu?
Sir, there exists an X in set A and B.
Okay, there exists. So from this step, what does it mean? There exists some X in
set A
such that
f of x is equal to y.
F of x is equal to y. Very good. And this belongs to this. And what does this imply? What does this imply?
There is the same element x in B.
Why should same element be there?
So because intersection.
No, we forget about intersection. We have y in f of A. That means you can find some x. Let me call this as x1. Instead of x, let me call this as x1. Some x1 in A such that, or I think I will instead of x1 I will write A. This is better. A in A such that f of A is equal to y. Let us use this notation. Okay, fine. Such that f of A is equal to y. And what does this imply? Second step.
Small b.
Yes.
There is b in capital B, such that f of B is y.
Y. Okay. Fine.
Y.
Right. Okay. That's correct. Now, let's look at what was our aim. Our aim was to show that y lies in f A intersection B. That means we are looking for some element x in A intersection B such that f of x is equal to y. That's our aim. What we have got is there is some A in capital A such that y is equal to f of A, and there exists B in capital B such that f of B is equal to y. Right? So, I mean, just to assist you, let me again draw the figure x, y here. This was y A, this is B, this is A, this is B, this is somewhere f of A, this is, let us say, f of B. We started with in the intersection. So this is my y. What I have got some element A here whose image is this. I have got some element B here, whose image is this. That's what we have got. Right? So can we conclude that A is equal to B? If A is equal to B, then what happens? Then this A will lie in A intersection B, right? If A is same as B, then it will be in the intersection. Right? We wanted to show that Y lies in F intersection B. What we have got is one in A, one in B. So is it possible? Can we conclude that A is equal to B? Is it possible for us to say that now A is equal to B? That may not happen, right? That may not happen. You can have two different elements which has same image, right? So from this, it looks like that now we have got into trouble in the sense that unless A is equal to B, there is no way that we can conclude that Y lies in F A intersection B. Okay, so it seems that this argument that showing that this is subset of this, we have hit some roadblock, right? We have encountered a roadblock. Okay. Do you understand what is the difficulty? Do you understand what is the difficulty? If we want to show that Y also lies in F A intersection B, it looks like we need the condition that A should be equal to B. We are given that F of A is equal to F of B because F of A is Y and F of B is also Y. So F of A is equal to F of B. When can we say A is equal to B? If F of A is equal to F of B, when can we say F A is equal to B? Come on, when can we say, when F of A is equal to F of B, when can we say A is equal to B? Yes? Rohini?
If F is 1, 1.
If F is 1, 1, very good. Why should it take so much time? It takes so much time. Right? So if F is 1, 1, then this, what we are saying will be always be true. Right? So when this F is not 1, 1, this, what we are saying that F of A intersection F of B may not be subset of A intersection B. So that's where the argument fails. In fact, that also gives me a way to construct an example where this will happen. This going to, so let us take, for example, I'll take, let us construct a map, right? So for example, I can look at, let us say this is my 1, 2, 3, 4, and for example, I can take a constant function, which is not 1, right? Let us take a constant function, right? Can we construct subset A and subset B such that F of A intersection F of B is not contained in F A intersection B, right? So for example, if I take A to be this and B to be this, this is my A, this is my B, then what is F of A? Let us say this is something. I'll call this as maybe, let us say Y1, this is Y2. This will be Y1, right? What is F of B? This is also singleton Y1. So what is A? What is F A intersection F B? This is always Y1. But what is A intersection B? A intersection B is empty set. Therefore, f of that is going to be empty set. Right? So this is not contained in empty set, isn't it? So therefore, this is an example where you have two subsets A and B such that and a function which is in this case a constant function. Of course, the constant function you need at least with two elements, such that f of A intersection f of B is not subset of f A intersection B. But what we observe that in case we impose a condition that if f is 1, 1, then this is true. Okay, so if f is 1, 1, then for every subsets A and B of X, what we are saying, f of A intersection f of B is going to be subset of f A intersection B. Okay, that's what. So the proof is now exactly similar, right? You start with an element y in f A intersection f B, right? Then y belongs to f of A and y belongs to f of B. Since y belongs to f of A, there exists some small a such that f of A is equal to y. Similarly, y belongs to f of B, therefore there exists some small b in capital B such that y f of B is equal to y. So you have got A and B in X such that f of A is equal to f of B. And since f is 1, 1, A is equal to B. Now, since A lies in A and A is equal to B and B lies in B, A also lies in B. Therefore, A lies in A intersection B, and therefore f of A, which is equal to y, lies in f A intersection B. Okay, so that is, so in case we assume that f is 1, 1, this is also true. Okay. Okay, just go through this argument. I'll give you some maybe 20 seconds. Just go through the argument already we have here. If f is 1, 1, then f of A intersection f of B is subset of f A intersection B. In case you get complete the proof, you can click yes. Only 3 of you. Okay, fine. So in case you still have trouble, please discuss. Okay, so what should be my next question? We have proved that in case f is 1, 1, then this follows. What should be my next question then? Are we happy with this, or should we look for something more? What should be my next question? Yes, anybody? See, we are exploring, so we have to keep asking questions. It is not that the teacher is saying that, okay, this is the result, prove it. After that, prove this result. No, we are not doing that. Yes, Chandrendu?
if f is onto, then it is true that f of a intersection f of b is subset of f of a intersection.
No. Of course, that is a valid question we can look at, but that's not something which we're looking for. Yeah. Whenever I have proved one implication, right? If P then Q. That we have proved. So, yeah, somebody else? Devika, what should be the next question?
Sir, the other part, for all A and B, subset of X, f of X intersection f of B is a subset of A intersection B, then f is 1, 1.
Very good, very good. Yeah, so we are looking for the converse of this, right? We have proved this, if this implies this. Now we will ask whether the converse is true. That means, if for every subsets A and B of X, if f of A intersection f of B is subset of f A intersection B, then can we say that f is 1, 1? Okay, that is what we want to look at. So what we are looking for, if for every subsets A and B of X, if f of A intersection f of B is subset of f A intersection B, then can we say that f is 1? F is 1, 1. Okay, so this is what you see that we hit a roadblock when this was not happening, when we have to do two distinct elements going to the same image. That is where the whole argument fell, right? So it is very natural to expect. Now let us try to prove this. So what is given to us now? This is what is given to us. For take any two subsets A and B, then this is true. We want to show that f is 1, 1. We want to show that f is 1, 1. So what is the definition of 1, 1 function? F is 1, 1 if you take distinct elements in X, its images should be distinct, right? So if I take x1 and x2 distinct, that is x1 not equal to x2, we have to show that f of x1 is not equal to f of x2. Or we can start with f of x1 is equal to f of x2. We have to show that x1 is equal to x2. Whichever way you want. So let us start with this. Right? So again, let me draw a picture just for your assistance. This is, I have x1, I have x2, and so this is my x, this is y, the function from here to here. So this will have some image. Let me call this as y1, which is equal to f of x1. This is maybe let us say x2, y2, which is f of x2. Okay. What is that we want to show? We want to show f of x1 not equal to f of x2. F of x1 not equal to f of x2. But we need to make use of the given fact. What is given here? For any two subsets A and B, f of A intersection f of B is subset of f of A intersection B. So we need to, if you want to make use of the given condition, we have to generate A and B, right? Okay, such that this happens. Okay, so how will you define your A and B? You are given two elements, x1 and x2, and x1 and x2 are distinct, right? And we want to check whether this happens. What should be your A and B? Very natural to construct. I want two sets, and we are given two elements, right? It should be quite easy. You can make some guess and then see whether that argument works. We are just exploring. So there is nothing, no harm if in case that argument fails at somewhere, then we will modify that argument. We will modify that set A and B. Okay, we are just exploring. So don't be afraid of making mistake. It is not true that if you once you have answered, then only you can say yes. No, you just start with anything. Yes, any of you? Akhila? What will you take A as?
I
What do you
take
want
A
to
as
take?
x1.
Okay, singleton x1. You want to set, right? So A is singleton x1. Very good. And what is B?
B is singleton x2.
Okay, very good. Singleton x2. So what is my f of A?
F of A is
If A is singleton x1, what will be f of A? It will be f of x1, no? Correct? This is singleton
Yes,
f of x1, right? What will be f of B?
singleton f of x2.
Very good. Singleton f of x2. Okay. Now let us make use of what is now A intersection B?
A
What is A intersection
intersection
B?
B is an empty set.
Very good. Why it is empty set? Because x1 is not equal to x2. Okay. So what will be f of A intersection B? Tell me.
F of A intersection B is
If A intersection B is empty, what is f of A? This is empty set. Very
set.
good. Okay. Very good. So, and what do we know?
We
f
know
of
that
A intersection f of B should be contained in now f of A intersection B. But this is empty set, right?
Yes.
So what does it say about when can this happen? F of A is my f of x1, singleton f of x1. F of B is singleton f of x2, and its intersection is empty. When does that happen?
When f of x1 not equal to f of x2.
Very good. This means that f of x1 cannot be equal to f of x2. Okay. Therefore, we have proved that in case x1 is not equal to x2, then f of x1 cannot be f of x2, and we have made use of this fact. Okay. So I wrote all the steps helped by Akhila. Thank you, Akhila. Very good.
Thank you.
Okay. Is this clear to everybody? Is this clear to everybody? Okay, fine. Wait. Still, most of you are saying yes. Very good. And don't you think that each one of you would have got the proof? This is quite natural way to construct A and B, right? So things are not different. Therefore, if I put both these together, what is the result we have proved? Both way implication is true, right? So what we have proved is we have got a characterization for 1 function. F from x to y, this is 1 if and only if for every subsets A and B of x, f of A intersection f of B is subset of f A intersection B. That's the result. So generally one would write this as a theorem. Okay, so this is a theorem. So we got this result just by exploring, right? It is from exploration we got this result. So this is another characterization of a function to be 1. If you want to check some function is 1, you can use this result also. Fine. So, right, let us. So we have not, we don't use here onto anywhere in this case. Okay, now let us ask another. So this is again your x, This is Y. Let us start with one set. Let us say I have set A. Okay. The moment I have subset A of X, I can look at its complement. Namely this, in this case, complement is this. This is the complement, which is X minus A. That's the complement. Right? So here also we can look at, suppose this is my f of A, this is my f of A. We can look at complement of this. The complement of this will be this. Right? Okay. And so this part is X minus A. Now let us take its image. Let us take image of this complement, A complement, which is X minus A. And on this side, what is this here? Right? So from here to here, you have function f. This, what we have marked, is nothing but y minus f of A. Right? So this is a subset of y. This is also a subset of y. Right? Again, we would like to check whether one is subset of the other, whether this is subset of this. Is this true? Or this is subset of this. Okay. That's what we would like to explore next. We would like to explore what happens to this. But before we explore this, let us look at some trivial case. When I say trivial case, if I say let us look at some trivial case, what does it mean? That means that I have started with the subset A. So what are the trivial subsets of X? Namely, I can take A to be empty set, or I can take A to be the whole of X. These are trivial subsets, no, of X. So if A is empty set, what does it say? What does it say? Then X minus A will be whole of X. Right? So f of X minus A is nothing but f of X. On the other hand, y minus f of A is empty. So f of A is empty. This is nothing but y. This is nothing but y. Okay. So we are looking for f. And what do we know already? We already know that f of X, this is a subset of y. So if this has to be equal to whole of y, if this is equal to whole of y, then the only way that can happen is when f is onto. Right? So if is in this case, I'm not saying in general, in this case, if A is empty and if these two sets are equal, then we conclude that f in case f is onto, this will always be true, because this f of X is going to be right. On the other hand, if you look at, however, this is always true. This is always true. So this, for empty set, this is always true. Similarly, if I take A to be whole of X, then X minus A will be empty, which is always subset of Y minus F of A. So there is nothing that we get. So it looks like that somewhere we need onto argument. Somewhere the onto argument is required. Okay. So let us try to prove one of this, and then see what we can get, whether we can again hit some roadblock. Okay, so let us look at y minus f of A. We want to check whether this is subset of f of X minus A. This is what we want to check. Okay, this is what we want to check. Okay, for any subset A. Now, first thing is, suppose this happens, suppose this is true. If this is true for, if this is true for any subset, right? If this is true for all subsets A of X, does it imply that f is onto? Does it imply f is onto? This is true for every subset, right? So in particular, it will be true for trivial subsets. Namely, it is true for empty set. So if I take A to be empty set, then f of A is empty, right? We already looked at this argument. So f of A is empty, therefore y minus f of A is y. And this is y is contained in f of x. But f of x is already contained in y, therefore f is onto. So this is true, right? This is true. And the proof is that take A to be empty set. Take A to be empty set, then this is always true. Okay, right. Let me just take another couple of minutes. Okay, right. So in case for every subset A of X, if this is true, then F is onto. The proof is follows by taking A to be empty set. So let us try to prove this without assuming anything on A, right? Without assuming anything on F, and then see what happens. So you take an element Y in capital Y minus F of A. This simply means that Y does not belong to F of A, right? That's what it means. Y does not belong to F of A. So now you look at the image, look at the diagram. I have somewhere A, right? This is my A, and Y is, and this is, let us say, F of A. Y is somewhere outside this. Y is somewhere outside this. Okay, what is that? We want to check whether Y lies in F of X minus A. Y should lie in F of X minus A. That means I should get some X somewhere here whose image goes to Y. But Y is anything. If it lies in F of A, then we have something in A which will go inside. But this is outside. Can we find X? We have no way to generate what should be X, right? But so that's where, so unless F is onto, we cannot find some X which goes to Y. So let us assume that F is onto. So if F is onto, right? Let us make this assumption. Let F be onto, right here, let F be onto. So if F is onto, then we know that there exists some X in capital X such that F of X is equal to Y. Okay, right. That's what we have. Then now we have some X. Now what is that we wanted to show? We wanted to show that Y lies in F of X minus A. That means I need to get X outside it. So does it mean that X is not in A? Right? If X is in A, what happens? If X lies in A, then this would imply F of X, which is equal to Y, will always lie in F of A. But that will be a contradiction, right? Because our assumption was Y is not in A. That is a contradiction. Therefore, X does not lie in A. If X lies in A, we are getting a contradiction. Therefore, X does not lie in A. So X lies in X minus E. So therefore, this implies that Y belongs to F of X minus E. Okay, right. So I went a little fast. Okay, so in this case, so what we have proved is, in case F is onto, then this is true. So that if you combine these two together, what result we have proved that F from X to Y is onto if and only if for every subset A of X, f of y minus f of a is contained in f of x minus a. Okay, that's what we have considered. So try to go through the argument. So in case f is, we have first proved that if f is onto, first we proved that in case this is true, then f is onto by taking a to be empty set. Second, we assume that if f is onto, we assume that f is onto, and from there we concluded that f y minus f of a is contained in f of x minus. So this gives you another criteria characterization of onto function. Okay, fine. So you could also look at what happens is the other way around, that is, look at f of x minus a. When will this be contained in? When will this be contained in f of y minus f of a? That is the second part we wanted to explore. What happens to this? And you can show that this will give you characterization of again 1, 1 function. Right? So f is 1, 1 if and only if for every subset a of x, f of x minus a will be subset of y minus f of. Okay, this is what you should. So this try to prove. This will give you as an exercise, and if you combine both two together, what will be the result? If I combine both these two together, then this will be the equality holds if and only if f is 1, 1 as well as onto. So f is a bijection if and only if for all subset a of x, f of x minus a is equal to y minus f. Okay, so we are able to characterize bijection function in terms of images. Okay, I think I already took more time than scheduled. I just wanted to mention these two again. Yeah. Okay. So please discuss sort of proof and arguments that we have done today. So I expect all of you to discuss, and in case you have any doubt, you can discuss with the mentors also. Fine. So let me stop.
Are there exercises?
Yes. There are some exercises which I have. Okay. All these. The last two exercise actually depends upon the inverse image. We have defined image of a set. We can define inverse image of set, and then again we can explore union. What happens to inverse images based on union and intersection? So I suggest all of you please look at the handout, the exercise set that we have given to you. In that there is one section to deal with inverse images. So that is very, very important concept. You will need that in a future course of mathematics that you are going to do. So please go through that section and then try to solve these examples. Unlike the images, inverse images are very nice guys. The inverse images behave very nicely with union, intersection, etc. Okay, so that's one thing I can say. Okay, so let me stop.
Do you have some message for the YouTube audience? We have valedictory at 4:30 tomorrow. Sorry. Not 5, 4:30.
Yeah, so yeah, right. Okay, so for YouTube viewers, I hope you enjoyed all these sessions and you learned this basic foundations, which is very, very essential for learning any higher mathematics. Again, some of the recordings possibly will be available maybe sometimes next week. So in case you have missed something, please go through and then try to solve all the problems, as many as possible. The problem sheet which is there on our MTTS website, in the download section under expository article of Professor S. Kumaresan. So please try to solve all those exercises. Of course, you can look at our book on foundation course in mathematics in case you get hold of it. And so thank you very much for joining. I hope you enjoyed. In case you have some question, you can write to us. You already, there are email on our website, but you can write to MTTS Trust, mttstrust@gmail.com. And we may even organize some sessions, live sessions for you. Thank you very much. We can stop. And there will be validatory function tomorrow at 4:30. The links are going to be provided on our website. So please join for validatory function. Thank you very much.